All right. So this is Math 3050 Discrete Math. And this is September 23rd, 2020. This is just our discussion meeting midweek. Jack, you made it. You said you weren't going to have internet.
Yeah, I managed to fix it somehow. I don't really know what I did, but it worked.
All right. Are there any questions before I throw questions at you? All right.
I have a question.
Yeah. Blake?
So I don't know if I'm doing this right. But whenever I go to try to watch a video, the video for like right?
Right. I'm
Which is fine.
Yeah.
I just want to make sure because I don't know. I was just having the issue where like it says it's there and then I hit it and it just goes to another web assign.
Yeah, that's my bad.
It's not. No, it's fine.
Yeah,
it's just I wanted to make sure I'm not screwing that up.
Yeah, I should not put the link in. I should not put that link in until the link is actually working. So yeah, sorry about that.
No, it's fine. I just wanted to make sure because I was like, why is it not working? So thank you.
Yeah, and sorry, my videos are sometimes not early enough. So yep. All right. Let me. Well, I want to throw out some questions. Again, my notes, I was thinking that we were meeting in an hour and my notes aren't quite done, but I think they're good. They're close enough to be able to be useful. So let me just switch over to sharing my screen. Let me see, share content. If I do that, can everybody hear me?
Yes.
Yes.
Okay. Now, what do you see? Do you see me?
I see you, but I also see the
all right
the slides.
I'm going to turn off my camera because I'm going to put my laptop down. All right, so now you should be able to hear me but not see me.
Yep.
I'm going to switch my laptop to landscape flipped so I can flip upside down and write on it. Okay, gotta flip it over. All right. So here are a bunch of discussion sessions, discussion questions, and I was going to put them each on their own page, and I was going to send them out to you. So let me see, where's I got a new version of this drawing program, and it's kind of bugging me. Just a second, where did my drawing tools go? All right, well, I had a drawing emergency yesterday, and I reinstalled this program. Here we go. Pin navigation menu. There we go. All right. So what about this first question? Do these two symbols mean the same thing?
No.
No.
Got a couple people who say no. Was that you, Blake, and Tin Zhao? Was that you two?
Yep.
So let's start with you, Blake. Let me insert a page here. Let me see if I can do that quickly. So, Blake, talk to me about those two symbols. What you say they don't mean the same thing. Why not?
Because 5 divided by 7 is hold on one sec. Okay, so like 5 divided by 7 is you're dividing 5 over 7.
Mm-hmm.
And I just know whenever you're doing 5, it's the opposite. Like they're the opposite, if that makes sense. Like it's going to be 7 over 5 and 5 over 7. So 5 over 7 for the first, and the second one is 7 over 5. And we're trying to see if it's an integer or not.
Hang on. Pretty close. Anybody else want to weigh in here?
Isn't it finding out how many times 5 can go into 7 and what the remainder is, and like that sort of thing?
Yeah. Let's just let me step back a little bit, though. I mean, just sort of what kinds of beasts are these? I mean, you know, if you're doing 20 questions, you'd have to say, you know, is it mineral? Is it plant? Is it, you know, what sorts of things? So, what kind of thing does this represent? Well, that's a number. So 5 divided by 7, 5/7 means a number. What about 5 vertical bar 7? Is that a real number? No, it's
no,
No.
it's not a real number.
no, it's a statement. It's the statement 5 divides 7. So it's a statement about the numbers 5 and 7. It could also be spoken this way. It's the statement that says 7 divided by 5 is an integer. So it's not the number 7 divided by 5. It is about that number. It's saying that 7 divided by 5 is an integer, but it's a statement, and it's a false statement. So both, you know, so this is false, and this is false. So the first thing that I wrote is a false statement about the numbers 5 and 7. This is a false statement about the number 7/5. All right, let me go back up. And Zhao, you said these don't mean the same thing, so maybe you can discuss so 2/6 and 2 vertical bar 6.
2 over 6 is like have like a 1 over 3.
Yeah, so that's a real number.
Yeah, and 2 vertical bar 6 means what if you 6 divide 2, well, you will get 3, and it means like 6 contains 3 2.
Yeah, but both you and Blake worked too hard. Remember that this symbol actually has a definition. So it just means this. It's spoken this way. 2 divides 6. It's also spoken 6 divided by 2 is
an integer.
Right. So this happens to be a true statement about the numbers 2 and 6. And this is this other one is a true statement about 6 over 2. So in both cases, well, so up here, this is a statement that happened to be a false statement. Down here, this is a statement that happens to be a true statement. But the thing is, it's very different from this symbol. This symbol just represents a number. This symbol represents a statement, and it's a statement about a different number. It's a statement about 6 over 2. But that doesn't mean that I'm saying that 2 vertical bar 6 is 6 over 2. That's not correct. 6 over 2 would just be a number. It'd be the number 3. What this symbol means, 2 vertical bar 6, is a statement that uses the words 6 over 2, but it says more than that. It says that 6 over 2 is an integer. They make this a little bit bigger. All right, let's go back up and look at some other questions. I'm not sure if I printed this big enough. Oops. I'm not able to slide my display around anymore. Oh well. Can everybody read this? Frick and Frack are arguing. Frick says that this is undefined. Frack says that this is true. Who's right?
Both.
Jinzhao, say more.
I said they are both correct. Like denominator. Like 3 over 0 is undefined, but 3 the bar 0 is a true statement. Is because it's 3 I'm not sure 3 divides 0, and another is 0 divided over 3 is 0.
Let's add another page here. So 3 over 0 is undefined.
That's true.
Yeah, so that's true. Now, so I should change that to blue. So Frack says that so he says that's true, and a number of you have said that that is a true statement. But let's to see why that's so it's a true. Well, so what does that really mean? It means that 0 over 3 is an integer is true. That's what Frick is saying, because this symbol here means these words. It also means that 0 equals, actually, I'm gonna, start color coding my letters. It's going to be tedious. Bear with me. So when Frick says, when Frack says that this is true, well, the way you assess that is you have to unpack what that really means. That green circled statement means this. It means that the number 0 over 3 is an integer. Well, that's correct, because the number, the symbol 0 over 3 represents the number 0. It also means this statement: 0 can be written as 3 times k for some integer k, and that's true. You could, the way you'd see that be true is you'd say that k is 0. So Frack's statement is Frick's statement up here is a statement about the symbol 3 divided by 0. Whoops. Whereas Frack's statement is, well, you could say it's a statement about 0 divided by 3. You could say it a number of different ways. Both of these things are mean the same thing as this. Okay, let me go back up to my list of things to talk about. Can everybody still see me? Or can everybody still see my paper?
Yeah.
Yeah. Okay. So how about this one? Sunny and Cher are arguing. Sunny says that, Cher says this. Who's right?
I think Sony and Cher are both right.
Yeah. Who's that?
That was Blake.
Blake. So so 0/5 so that is the real number 0. So that's true. And then this statement, let's unpack that. So that's a defined term. So what does that term mean? That term means that 5 divided by 0 is an integer. And that's and so Cher is saying that this is false. And that's a true statement, because this is a false statement. So when Cher says that it's false, she's actually saying the right thing. All right, let's go back up. For what n is that true? And for what n is that true?
Are you wanting us to answer?
Yeah. Anybody have a comment about that?
I do, I think. I hope. So for the first one, I think n could be any integer. And for the second one, n would have to be 1.
Very close. Anybody notice there's one small mistake? Who is that speaking?
Jana.
Jana. Jana made one very slight mistake. Anybody catch it?
Would it have to be a positive integer?
Oh, great question.
I think for the no, I don't think it need to be positive for first one. I think it can be any number for the first one. Any integers for first one, but second one should be positive. Well, yeah, 1 is positive. I don't know.
Oh, the second one should be positive or negative 1.
Exactly. So, so let me circle these. I'll circle this one. For the left one, 1 vertical bar n is true for, well, let me just insert a new page. I really wish I had done these on separate pages. So let me see. So Jana's saying that 1 vertical bar n is true for any integer n. So what does that really mean? It means that, whoops. So 1 vertical bar n means that n divided by 1 is an integer. And that's true. Good. Now what about this one? That means that 1 divided by n is an integer. And that's only true when n is plus 1 or minus 1. All right, let's go back up and look at the second question, or similar question. For what n does that happen, and for what n does that happen? Anybody want to comment on that? Got a couple people lurking there who haven't spoken up. Anybody want to speak up who hasn't spoken up yet? Anybody can speak up.
For first one, the n should be 0. Second one can be any number.
Let's go down and have a look. So 0 vertical bar n means that n divided by 0 is an integer. Jinzhao, you said that that's only true when n is 0. Is that correct?
Well, yeah, that's what I said, yeah.
Do you want to stick by that, or do you want to change your mind?
Well, if I want to change my mind, then it's gonna be this is a false statement.
Yeah, so it's never true. Can't divide by 0. Even 0 divided by 0. Okay, what about this one? So that symbol,
and
n vertical bar
cannot
0.
be, I will change my mind. Is n cannot be 0, and
Good. Good. So this is true for all n except n equals 0. So in other words, it's like I should just say, maybe I should say this way. Oops. So this division symbol is this divides symbol is a tricky symbol. You have to read it very carefully and be aware that it does not mean the same thing as the slash. It is a statement about about a fraction involving 5 and 7, but the fraction that it's talking about is not 5 divided by 7. The fraction that it's talking about is 7 divided by 5. But this symbol does not mean 7 divided by 5. It means a statement about 7 divided by 5. It's this whole thing. So it's a statement, not a number. Okay, that's one thing that I wanted to talk about today. Now, I want to go back to something Tin Giles said a while ago, having to do with 0 over 0. Now, from now on, I'm going to be color coding my fractions a lot of the time. I'm going to be color coding the thing in the numerator green because it's like grass growing above the earth, and I'm going to be color coding what's in the denominator as blue because it's like it's underwater. So why not just declare that 0 over 0 is 1? Why can't we just declare that? It's a common enough. It would improve a lot of students' grades because a lot of students make the mistake of saying that 0 over 0 is 1. And it's not. But why don't we just change the rules and say that 0 over 0 is 1? Now, there's another related question. Look at this equation here. That green 0 can be written as the blue 0 times the number 1. And so since I have an equation of that form, that green 0 is equal to the blue 0 times some integer, you might think that that would mean that this symbol is true. But the definition of what that symbol means, that definition says we're not allowed to have a blue 0 on the left side of the vertical bar. That is, this is never true. Not even 0 vertical bar 0. Why not? Now, these questions are related because, you know, if we're allowed to have this symbol, that would be saying that that green 0 divided by the blue 0 is an integer. So this question is related to that question. Why not just say that that green 0 divided by the blue 0 is the number 1? And then we could say, you know, this is okay because this is true. Does anybody have a comment about why that? What's up with that? Can we just do that? Just change the rules?
I don't know what the official like scientific way to say this is, but when I was younger and we learned how to divide, like the first time we learned what that was, you would just have groups of like M&Ms or random crap, and then you'd sort it into other smaller groups. So like when you take something, let's say you have like 5 pencils, and they tell you put it into, divide it by 0, like put it into 0 groups, it's like not even possible. Like you can't just like make them go into non-existence. So if you had like 0 pencils and they're like, okay, put it into 0 groups, that doesn't create a pencil. It's just, I don't know what the scientific way of on paper of wording that, but it doesn't like, it just doesn't work. You can't put things in sort them into 0 groups. It either like implies that you're ripping apart the fabric of time and turning it into nothing, or you're creating matter. And we just don't do that.
It's making me think about M&Ms. Who's that speaking?
It's Eden.
Eden, hi.
Hi.
I agree with Eden. I was
that?
just going to say, it's Blake. I was just going to say, I mean, when you really come down to it and think about it, when you have 0 quantity of anything, you can't just get 1 from that. Like, I like how she said the M&Ms. Like, yeah, I remember doing all that, and that actually thinking about it, that really helps with this, because you would assume like if you put 10 or if you put a 1 in front of both those numbers, it's equal to 1. But I don't know. I just wanted to chime in there.
Yeah, that's why I wanted to bring this up, because there are all these. Go ahead, Tenjo.
I would say like probably we need to add another thing is called a natural number, which is, well, I know natural number only have a positive part, it not including 0. So 0 for natural number, it doesn't have a meaning. When you try to have something divided by two non-meaning things cannot be like timed, divided, or minus. Well, yeah, that's what I'm trying to say.
Okay, yeah, so it's neat to hear all these because I mean it's hard to sort of, well, think about this. It's I love it that you all have thought about this and have ways of explaining it. But what if you're in a conversation with somebody and they say, "But I just want to say that's true," and they're convinced that they have no problem with this, and so they like your story about the pencils and the M&Ms, but they say, I don't care. I'm going to say that this is 1. I don't care about pencils and M&Ms. That I'm not troubled by that. So if they don't find this troubling, they're not troubled by the story about the M&Ms, where do you go from there? Well, the idea is you have to go back to the fundamental definitions of the real numbers. I mean, there are these axioms for the real numbers, and that's in the book Appendix 1. And it's these 6 axioms. Addition is the real numbers are a set, and they have 2 operations, addition and multiplication. And those operations satisfy these rules. So addition and multiplication are both commutative. Addition and multiplication are both associative. You can move parentheses around. Then we have the distributive law. That has to be true. And that has to be true. Of course, some of these are redundant. I mean, you really don't need to have the second one, because if you have the first one and you have commutativity, then together, those would actually give you the second one. So you don't really have to list the second one explicitly, but it's a law. And then the identity element is crucial. There's two special real numbers. One is denoted 0, and it has the property that 0 plus any number is just that number. And then there's another special real number that's called the number 1. That's called the multiplicative identity, and it has this property. 1 times any number a is the same as just a. And then additive inverse. So for each number a, there's another real number which we give the symbol negative a. And what it means is this special number negative a has the property that when I add it to a, I get 0. So negative a, we don't get to negative a by thinking of negative 1 times a. We get to negative a by this axiom. It's this special thing that's guaranteed to exist. It's called the additive inverse. Later on, we get to discovering that, oh, negative a is the same as negative 1 times a. But negative a comes into existence first as one of the axioms. And then here, reciprocals. For every real number a, there is a real number that's denoted this way, 1/a or 1 over a. And it's called the reciprocal, and it has this property. If I multiply a by its reciprocal, I get 1. So again, we don't get to this equation by saying, oh, that makes sense because a divided by a is 1. Well, no, that comes later, the idea of division. What comes first is this idea that every non-zero real number has something that's called its reciprocal, and it's denoted that way. And it has to satisfy this equation. So notice that, go back up to this. Why not just declare that green 0 divided by blue 0 is the number 1? Well, what does that really mean? Green 0 divided by blue 0. Let's see if I have this. So if you want to say that green 0 divided by blue 0 is the number 1, what that really means is this, that green 0 has a multiplicative reciprocal. It's this thing that's denoted this way, and it behaves this way. So if your friend who's really comfortable with this idea that they just want to say 0 over 0 is 1, what they're really saying is that 0 times its multiplicative reciprocal is equal to 1. And so that's saying that, it means that there's this number that behaves this way. And so that means that the number 0 has a reciprocal. So let's go back up and look at the axioms. The axioms guarantee that any number that's not 0 has a reciprocal. They don't guarantee anything about the number a equals 0. So they guarantee, they don't guarantee anything about the number a equals 0. They don't say it has a reciprocal. They don't guarantee it, but they don't explicitly forbid it. So the question really is, when your friend says they want to just declare that this is true, is it possible? Is it possible that 0 could have a reciprocal, even though it's not guaranteed by the axioms? So the answer to that question comes in the theorems of real numbers that immediately follow the axioms in your book. So this is from Appendix A1 as well. So these theorems are statements. They're not included in the list of axioms because they don't need to be. They can be proven true as a consequence of the axioms. So there's a whole list of these. I only included the first 6. The first 6 theorems. And look, one of the theorems is this, 0 times any number, A is an arbitrary real number. Theorem 6 says that 0 times any number has to equal 0. So you can tell your friend, look, this is about as fundamental as it gets. The rule is that the rule, the very foundation of real numbers, you have this theorem that says 0 times any number has to be 0. And so this can't be true. That can't happen. 0 times 1 over 0, 0 times its reciprocal equals 1. That's impossible. We have this theorem 6 that basically says 0 can't have a multiplicative reciprocal. So that's it. It's impossible for the number 0 to have a reciprocal. So it's impossible to have this be true because that would violate theorem 6. And your friend could say, well, I'm just gonna throw out theorem 6. Well, you can't throw it out because it's a theorem. It's proven that it's true as a consequence of the axioms. But the thing is, it's not just this one little thing that gets messed. That it's not just this one little rule that gets broken. If you want to claim that 0 has a reciprocal, that would violate T6, theorem 6, but it violates other stuff as well. So for instance, look at this calculation. Start with the number 7. Now 7 can be written as 7 times 1 because this is a property of the number the number 1. It has the property that any number is the same as that number times 1. And then this this equal sign is true because your friend who wants to say that 0 over 0 is 1. And it's going to be a guy. A guy is going to say something like that. All right, and then what's this equal sign? Well, this equal sign just reflects the idea that when you write this symbol, the meaning of that symbol is actually this. So in other words, A over B actually means A times the multiplicative reciprocal of B. So this is the definition of what the symbol A over B means. Okay. And then what about this equal sign? Can anybody tell me why this equal sign is valid? This is associativity. Because remember, if you go back up to the rules, the axioms say that real number multiplication is associative. So if I have A times parentheses BC, I can rewrite that as A parentheses B times C. So that's what happened in that step. I had 7 times parentheses 0 times parentheses 1 over 0, and I moved the parentheses over here. So that's just associativity of multiplication. And then what's this? How do we justify this? Replacing 7 times 0 with 0. Well, that's just a property of 0. The number 0 is the number that's, well, this is by theorem 6. theorem T6 says that 0 times any number is 0. And then what's up with this? Well, let's see. Now, wait a second. How did we do this? Well, we did the same thing there that we did over here. To write 0 over 0 just means 0 times its multiplicative reciprocal. So this is just the definition of what the symbol A over B means. Again, when you write A over B, it just means A times the multiplicative reciprocal of B. Okay, and then we get to this. Oh, now we've got this crazy symbol, which this guy is insisting is equal to 1. So your friend who's very stubborn and says that, I don't care about pencils and M&Ms, I'm just going to declare that I'm going to be all right with that. Well, you can, not try to convince him regarding M&Ms or pencils. You can just say, well, if what you're saying is true, then that's going to have to mean that 7 equals 1. And that's just nonsense. So it's not just theorem 6 that gets violated. There's all sorts of stuff that wacky stuff that would happen. So in the axioms for real numbers, they don't specifically forbid that zero could have a reciprocal. They just don't guarantee it. They say every number that's not 0 has a reciprocal. But it turns out that they don't have to say it because it's a theorem. 0 doesn't have a reciprocal. 0 times any number has to equal 0. All right, that's a long rant, sorry. I want to go on and introduce something coming up in today's work. So this is section, any more questions about divisibility before I go on?
It's not really a question, but in the guy's argument, he it's still not great because he kind of contradicts himself because he says 7 times 0 is 0 because he follows the theorem that he doesn't really think is true. Yeah, and then at the end, it's 0 times 1 over 0. And I'm like, but you already admitted that 0 times anything is 0 because you canceled out 7, but you didn't do it later on. So if anything, it would be 0, but so it's wrong anyway.
Yeah, so it's not. So yeah, it does come down eventually to violating T6 again, because T6 theorem 6 is in this argument. So I guess you could say, well, if you're okay with violating theorem 6 here, then that means you're going to be either. Well, I guess if the guy says he wants to throw out theorem 6, then this whole computation would have to end right there, and you'd have to say, well, so what do you want that to mean? So yeah, it gets weird. I mean, all these arguments are weird, but yeah. Any other comments before we go on? Any other comments about divisibility? Main thing I wanted to get at is these things, the importance of reading these symbols carefully, realizing that symbols like this represent numbers, symbols like this represent statements about fractions. So this is a real number, this is a statement that can be true or can be false. All right, I don't want to talk much longer. I want to talk about content from the next section. This is 4.5. So look at this collection of equations here. There's an infinite list of equations involving a green 71 and a blue 9. All these equations are true. So is any one of them more special than the other?
$71 equals 9 times 7 plus 8.
Exactly. So this is the special one. Why? What's special about that one?
Because, oh my gosh, because 71 have 7, 9 in the 71 and is left 8. But if we do 6 times 9 plus 17, but there's a 9 in the 17. And
Yeah, I'm going to say this a different way.
yeah.
It's a special one because this. That red 8 satisfies that inequality. None of those other red numbers satisfy the inequality where you have, you put a 0 here and you put that blue 9 there. Let me, and now this is, I ran out of time. Let me see if I can add some more pages. Let's do I'm going to copy this a bunch, see if I can do my lasso again. Okay. Oops. So look, in this row, this is the special one. Because if I build the inequality with 0 less than or equal to that red 1 and then less than the blue 9, that's true. So this is the special one. And let's do one more batch. Let's go And let's copy that one. So let's see, let's do so notice that in this string of equations, again, there's an infinite collection of equations like this involving the green 72 and the blue 9. There's only one special one. This one satisfies the inequality. I put down the number 0 less than or equal to the red 0, and then it's less than the blue 9. So, so this is true. If I try to do that for the next one, notice the next one fails. That's false. So I'm allowed to have 0 equals 0, but I'm allowed to have that red number equal 0, but I'm not allowed to have the red number equal 9. Well, so this is called the quotient remainder theorem. And what it says is this. I'm going to quantify it. So, well, maybe I'll say it in words first. So for every integer n, green n, and every positive integer d, that's a blue d, there exists exactly one integer q and one integer r, red r, such that two things are true. First of all, that green n can be written as that blue d times that black q plus that red r. And the other thing that has to be true is that inequality. So let's write this in symbols. So for all, I'm going to write n in this set of integers. Write that in green. And what about it? Well, let's see. There exists a d that's got to be a positive integer. Can't be 0, can't be negative. So that's denoted z, z plus. And what about it? Well, let's see. There exists a q and an r that are in the integers, such that what? Well, those two things have to both be true. So green n equals blue d times black q plus red r. So that's one thing that's got to be true. And the other thing that's got to be true is that inequality. Sorry. So now these terms are called let's see, what's the jargon? The letter Q is called the quotient, and the red R is called the remainder. Anybody know what's in the blue D is called the divisor? What's the N called? Well, anyway, R is called the remainder. Let me give you an example. How many people are still out there? Say hi if you're still there.
Hello.
Hi.
Oh,
Yes.
still there. Good on you. All right. Well, so the last thing I want to talk about is what we're going to do with this. I want to talk about one rule of inference. So this rule of inference is called proof by division into cases. Let me see if I can find that in our book. It should be in section 3. Actually, maybe in chapter 2. I want to make sure I use the same terminology that the book uses. So this is from the book, page 76. And the rule goes, the rule of inference goes like this. So the rule says P or Q is true. If P is true, then R is true. If Q is true, then R is true. And so therefore R is true. So it's kind of like, you know, damned if you do, damned if you don't. One of these things is true. Maybe they're both true. That's what the P or Q means. It's the inclusive or. And so if you know that one of those things is true, and if you know that if P is true, then R is true, and if you know that if Q is true, then R is true, then you can say that R is true. And this generalizes to more variables. All right, so what do we do with that? Well, we use that that rule of inference in conjunction with the quotient remainder theorem. So let's go back up. This is the quotient remainder theorem, I'm going to abbreviate QRT. So the quotient remainder theorem says that there's exactly one integer, one red integer that satisfies all of this stuff. So there's one integer q, the black number q, and one integer r, this one special remainder that makes all this stuff true. And that's the sort of fancy way of saying that in all of these lists of equations, there is exactly one special equation. So I'm going to do something here. I'm going to say let m be an integer. So what does the quotient remainder theorem say so QRT? And what does that say about d equals 3? And so let's I'm going to change this. I'm going to change that m to a green n. Well, it says the quotient remainder theorem says there is exactly one integer q and a red r, such that, well, that green n, whatever it is, can be written as that blue 3 times a black integer plus that red r. And also, what about that red r? It's got to be between 0 and 3. It can be 0, but it's not allowed to be 3. This has to be a blue 3. So that's what the quotient remainder theorem says in that particular case when you apply it to the case where d is the number 3. Well, that means that either n can be written as 3 times q plus 0, or maybe n can be written one of these other ways. It means that one of these 3 things has to be true. So for instance, if n is the number 15, then we're going to have 15 equals 3 times 5 plus 0. If n is the number 16, then we're going to have 16 equals 3 times 5 plus 1. If n is the number 17, we're going to have n equals 3 times 5 plus 2. But if I get up to n equals 18, then we're back to another one of these forms. So if I have any random unnamed integer or unknown integer n, I know that one of these 3 things has to be true. So so what do we get with this? Well, if we use it in conjunction with the thing that I was just talking about, the proof by division in the cases, we can do neat things like this. Prove that the product of any 3 consecutive integers is divisible by 3? Well, so how do we prove that? Well, you start by noting that if you have 3 consecutive integers, then they can always be written in this form. Remember what I introduced this in an earlier video, that a generic way of writing 3 consecutive integers. I don't know which ones they are, but they can always be written that way. So their product is n times n plus 1 times n plus 2. So the idea is that one of these numbers is going to be a multiple of 3. You got 3 numbers in a row, and every 3 numbers, if you go up the list of integers, every third one is a multiple of 3. So one of these numbers is a multiple of 3. That means the product is going to be a multiple of 3. Well, so that's the gist of the quotient remainder theorem. So let's go back to what we had on the previous page. The quotient remainder theorem says that one of these 3 equations is true. So I can just write that, the quotient remainder theorem, with using a blue D, that's the number 3. It says that that green n equals 3 times some number q. Or maybe it's this case, n equals 3 times q plus the number 1. Could be that case, or it could be this case. So one of these 3 cases is true. Well, so in my proof, there's statement 1. Statement 2 is the quotient remainder theorem with D equals 3, which tells us that one of these statements is true. Now look, let's go back up to the proof by division into cases. We've introduced an OR statement that we know is true. So that's part of our job. We've introduced the OR statement. Now we have to show that in either of those cases, R is true. So what does that mean? So let's do the case 1. Let's suppose that that's true. Well then, n plus 1, n plus 2 would be 3q plus 1 times 3q plus 2, and that's a multiple of 3. Or maybe I should say, if n is that number, then this product is divisible by 3. Okay, that's my statement 3. Let's do another statement. So case 2 if n is the one of the other cases, like suppose this is the case, if this is the thing that's true, and I just substitute that into this expression for the product of the three consecutive integers, then I get this result. And notice that this is a multiple of 3. So that means that this whole thing is divisible by 3. Okay, let's do the third case. Oops, that should be statement 4. Statement 5 should be case 3. Suppose that it's this thing that's true. Oops, sorry about that. So if that's the thing that's true, then n plus 1 times n plus 2 would be that stuff. I'm making a mess of this, sorry. So when I substitute that quantity into these expressions down here, I end up with this. And so that's 3q plus 2, 3q plus 3, and this is 3q plus 4. And you see that this one is a multiple of 3. And so because that's a multiple of 3, that tells us that the whole thing is divisible by 3. So look, we have 3 cases, and in every one of those cases, the product turns out to be divisible by 3. So the conclusion is we see that since n times n plus 1 times n plus 2 is divisible by 3 in every case, we conclude that it's divisible by 3. So let's go back up and look at our proof structure. proof by division into cases, we have to introduce an or statement and then show that if we're in the case of P being true, then some conclusion R is going to be true. And we also have to show that if Q is the thing that's true, that is, if we're in the other case, then R is also true. And then we can conclude that therefore R is true. So look, we did a proof where we got our OR statement from the quotient remainder theorem. So that's our great big OR theorem, our OR statement. And again, it comes from the quotient remainder theorem. And then we proved that in every case, if we're in the first case, then the thing is divisible by 3. If we're in the second case, then the thing is divisible by 3. And if we're in the third case, then this thing is divisible by 3. And so we had a proof by division into cases with 3 cases. When I said that this generalizes into more cases, we did an example with 3 cases. And then we have to say the conclusion very clearly. This is the therefore, since each of those if-then statements was verified, then we can say the conclusion. All right, so I've gone on way longer than I wanted. Let me stop sharing. All right, just a couple of you left. So again, sorry for running so long. My light's off. All right, well, so that's the idea of the quotient remainder theorem. And let me turn my light on. Sorry. That's the idea of the quotient remainder theorem and the idea of proof by division into cases. That's both stuff. Both those things are from section 4.5, which is for tonight's homework. If there aren't any questions, I'll wrap this up and turn off the recording.
Just no questions. Just I was going to ask, when do you think you're going to have the video up for 4.3?
I've got to get it done in the next couple of hours because I've got to run to a soccer game after that. So
no worries. Just want to. No, that's fine. Thank you so much.
I'll put this up right away. This meeting video will go up. Well, it's always mysterious to me how quickly they show up, but this will show up and I'll post it as well.
Thank you so much.
Thank you all.
Thank you.
Bye.
Thanks. This was super helpful.
Good.